In this video, we are going to introduce external direct products. So why are we studying external direct products? What's the point of direct products? Very simply put, what we want to imagine is that we have two things. In our example, our things are going to be groups, but the idea of having two separate things and wanting to put them together somehow is a very common mathematical concept. Now our external direct product is going to take our two things, no matter how dissimilar, and shove them together in a very straightforward and almost superficial way. But that's very good for us from a theoretical perspective because it's going to make these objects easy to interact with and easy to study. So let's see this example of taking two very different things and shoving them together in an external direct product fashion. So here, my two different things are going to be two different groups. I've actually chosen two different groups that do kind of have something in common. They're both these finite cyclic groups, Z mod 4Z and Z mod 3Z, but they are different sets of elements and their operations are different. In the purple group over here, G1, we're adding modulo 4, and in our black group G2, we are adding modulo 3. Despite the fact that both of these groups are using some mechanism of addition and they're both finite groups here, you're truly free to take direct products of any types of groups you want. So you could have a Z mod NZ and you could have a U group. You could have an infinite group over here and a finite group over here. You could have a non-abelian group on the left and an abelian group on the right. They can be as dissimilar as you would like them to be. The mechanism for combining them, set theoretically, is just to take a Cartesian product of the two sets, where we think of the elements of this new group, the external direct product of G1 and G2, written with this O plus symbol in the middle. We just list all possible combinations of elements from G1 and G2 in an ordered pair mentality, where the first element of the tuple is from G1 and the second element of the tuple is from G2. So set theoretically, the new group is the Cartesian product of the two groups. However, because the object that we're dealing with is not a set and is in fact a group, we need to discuss what the binary operation on this group G will be, and then I'd like to discuss the other two group theoretic properties of identity and inverses. So remembering that our group G is here listed at the top, we ask things like, what is the new binary operation on this set G? If I pick two elements out of this set at random, how do I combine them via my dot operator? If I want to know how to combine this whole element with this whole element, I really only have a way for combining purple elements and black elements individually. And that's precisely how I'm going to define overall the method of combining these two elements. Let's first combine the purple elements in the way we know how, adding them modulo 4 in this example, and let's second combine the black elements in the only way we know how, in this example, addition modulo 3. Or more generally, let's combine the elements in the first component with the operator of the first group, and let's combine the elements in the second component with the operator of the second group. And that example is given right here. I may be interested in the identity of this new group G. Again, we hope that the identification of the identity is somewhat natural. What on earth element of this group seems like the most likely candidate for being the identity of the overall group? It's probably the individual identities of all the groups I've combined in this fashion. So it's probably the purple identity followed by the black identity, or the identity of the group 1 followed by the identity of the group 2, and so on. That overall is the identity of the group G. How about what we should do to find the inverse of an element of this new combined group? It's kind of the same mentality as the first part of the problem. I understand the idea of taking inverses individually in each of my groups, and therefore that's what I'm going to define the overall inverse operation to be. If I want to know the inverse of an element of my Cartesian product, I'll simply separate the inverse operations up component-wise. So I'll ask for the inverse of that purple element inside the purple group, and I'll ask for the inverse of the black element inside the black group. Or in other words, overall, my inverse operation is found by finding individual inverses inside the groups G1 and G2, and listing that as an ordered pair. So the idea is I've combined my elements in a very superficial way by taking this Cartesian product. Whenever I need to do anything, I just split that up back into the original groups where I already had mechanisms for doing all of the things that I want to do. In my separate groups, I perform whatever action is necessary, combining elements, finding the identity, finding inverses, and then in the end, I put them back together in this superficial Cartesian product typed way. And so this very simple mechanism for combining elements makes each of the operations inside the large group also very simple and easy to understand. Even though finding orders of elements is not built into the definition of a group, I'd still like to think about, in an external direct product, how do I compute the order of any one of these elements? Let's take as an example the element 2, 1. Since we've already discussed how we're going to combine things via our group operation, and computing the order of an element is simply a process of combining that element with itself many times under our group operation, we're perfectly capable of doing this at this point. We know that this particular element I've selected, 2, 1, is not the identity of the group. Our identity of the group is 0, 0. So what we need to do is take this element and combine it with itself several times until we've arrived at the identity of the group. Taking this element and squaring it is akin to squaring each element individually. So 2 plus 2, mod 4 is 0, while 1 plus 1 is 2, mod 3 is still 2. And we continue in this way. 2 cubed in z mod 4z is the same as 6, which is equivalent to 2 mod 4. 1 cubed inside the group z mod 3z is 3, or 0 modulo 3. So we get a 2, 0 here. And we would continue in this way until we've reached 0, 0. Because we are doing everything component-wise, we see that any element raised to the nth power inside of our group G is simply going to be the first component raised to the nth power interpreted in the first group, the second element raised to the nth power interpreted in the second group. And we see from this formula that we should expect to arrive at the identity when we've reached a multiple of the order of the first element and a multiple of the order of the second element. And given that we would like to know the order of this element, and we'd like to know the first time that we reach the identity throughout this process, we conclude that the order of any element inside of this group will happen at the smallest multiple of the orders of the individual elements. In other words, the least common multiple of the individual orders. And this formula is very useful for determining the orders of elements in direct products, which is something that we'll do very frequently.